0.26, this says 0.59, so you round it up. You round it to 0.59.
Come on, it's going to be okay. Alright? That's the molarity. And you might be wondering, Mr. Stan, are you going to take off points if we're just a little bit off over here? No.
You're not talking about
Oh my god.
What did I say about that?
I'm like, hey, look, that's first.
That's what I heard. Let's. Any questions about this right now before we move on? This is a difficult kind of question I can ask you. Okay, yes, let's do that. Molo equals min ln.
Wait, can I just get something so stat?
What's that?
Can I just get something clarified?
Sure.
The M in molo and big lid stands for molarity.
The big M, yes. Big M is molarity. Always big M, big molarity. Okay. All right. Molo equals min ln. What the heck does this mean? Old and new. That's what the O and the N stands for, right? Min ln. Right? Old molarity of the old solution. That's right there. The liters of the old solution. They times them together and they equal the same product over here of the molarity of the new solution times the liters of the new solution. That's what the equation means. So, in any question I can ask you, I will have to give you, or at least give you the tools to get, 3 out of the 4 variables here. So that means I can give you this, this, and this, or possibly this, this, and this, or maybe this, this, and this, or this, this, and that. I've given you every combination of question I can possibly ask you. So, with that, let me give you one of those possibilities. And we should be able to solve this. The only difficulty about these questions is usually when people are reading the questions, they get confused with the words. They get confused about what you're diluting, what's the new, what's the old, and they start doing crazy things and multiplying and adding things, and I don't know why the heck they do that, but they do. So all you have to do here is just keep it in your mind that it's somehow going to be related to this. When you hear the word diluted, or new solution, or old solution, I've worked hard to keep the language the same so it wouldn't confuse you. So if you start with old solution, and you've given molarity and liters, and you say, I know what the new molarity is, but I don't know what the new volume is, or the new liters are, then you should be able to find that last ln. Okay? Yeah?
Diluted is what again?
Diluted means to take something from a really high concentration, like the Gatorade that we made yesterday, and put more water into it, so you dilute the sugar in the Gatorade.
So when you see diluted, that means older.
So the diluted part is always going to be the new stuff. So when you say something's, that's a good question. When something is diluted to, that means the new thing is going to be the thing that it's diluted to. Right?
Right.
Right. So let's say that who am I going to talk about today? I say Pierre.
Yeah.
Pierre has how many molar solution?
23. 12,622.
12,672. Is that what you said? And what kind of a solution is that? What do you have in there? Like what chemical?
Sugar. Francium.
Okay, a francium. Of F. Is it F or FR?
FR.
FR, of course. I'm sorry. Of francium. Oh, it's FR. Okay, we got FR right there. Okay, so that's how many. That's the molarity of your solution right there. And how many liters do you have?
2.
And 2 liters of this. Yes. Of this solution. These are the kinds of words I use. Okay, so what we've done right now is we've dissolved francium so that it's 12,672 molar. So it's got a molarity of this in this volume of solution.
So we've got molar.
Right? So that's a very, very, very concentrated solution of francium. Yes, it's very, very concentrated. Now he's going to dilute this. So by diluting, all you have to do is to make sure that you increase the volume. Okay, so now Pierre dilutes this to how much liters? It has to be bigger. 23. So there it goes. Here, do it. 23 liters. How do you set this up? Well, you plug these things into MOLO and the LIN. And you're going to find the min. Okay, so now you see it? We've got this right here. This is going to be the MO.
Fine.
The bad MO. Now we've got this other liters right here. This is going to be the low. Right? Does color help? Now we've got this green over here as liters. That's the new liters. So we just don't know what the min is. So let's set this up. This is pretty easy. Let's do it. 12, 6, 7, 2. And you don't need to even use units with this because it's a ratio here. So now we have liters, so it's times 2 equals, we don't know what the mn is, and the liters is 23.
Oh my god.
So to solve this, what do you need to do?
Divide by 23.
Yeah, divide both sides by 23. Divide this side by 23. Alright, and you get as your final answer. Let's try it.
1.9.3.
I'm going to trust you. 11 point what?
1,101.
0.913.
913.
Big
Are you sure about this?
I am positive.
Okay. Big M.
Big M.
This is our big MN. This is our new molarity here. Okay? That's it. That's it for MOLO Min Lin. We're good? Fantastic. Now, let's talk about endo-exo. This is going on. Yes?
Would you give us like a question where we have to convert milliliters to liters and then do milliliters?
You could. I could do that.
Did you already do this?
Yeah, I already made it.
Or fine molarity like we had to do the other day in the worksheet.
Fine molarity, and then
plug it in.
you could do that, couldn't you, though?
Yeah.
You just do the steps we did just before this question,
Yeah.
and you can find molarity, and then you can find that would be a really hard question. It's like 3 steps. So that would be, yeah, it would be something like around a bonus, or the bonus is going to be fun. You're going to like it. I'm giving you this. The bonus is actually the same. Yeah, I won't tell you. Let's talk about endo-exo. Let's talk about the endo. Let's talk about the exo. All right.
Yeah.
I'll erase this. We're so good. We're still rolling. This is great. Now, endothermic reactions. I'm going to give you a couple examples here. A plus, oops, I'm just going to do this. A goes into B. A goes into B. Endothermic reactions. Endothermic reactions are reactions where you have to put in heat to make the reaction go. So it's always going to be a part of the reactant to be endothermic. Exothermic, heat is always a product. Okay?
Which one is on top? Exo.
This is endo, this is exo. This is endo, this is exo. Heat is exiting the reaction here. Heat is entering the reaction here. If you don't remember that, it's a good way to remember. Now, I can ask you lots of questions about this. I can ask you, the easiest kind of question is the one that we practiced before with the graph, where we have time on this axis and we have energy on this axis, and we have the reactants right here.
So endothermic, the heat is going in.
So heat is going in for endothermic, heat is going out for exothermic. So if the products are up here, that means that the reactants would have had to absorb energy to get up there, right? So that means you'd have to plug heat in. So this whole process right here would have to be, this would have to be endothermic. Heat's going in. I'm going to use a different color for the other one. Now let's, so that's, wait. Okay. That's heat going in. Okay. So that right here is endothermic. I'm going to do heat going out now. Heat going out. Heat is going to now be leaving the system, and the products are down here. So at the same point of reactants, but now heat is going to be released. Heat is released. So this is exo, right? Definitely exo. Heat's being given off as a product. Now, here's some tricky questions. Ready for this?
Oh god.
Okay, I'll wait. Let me know when you're ready. Okay. So, imagine now that you are freezing water. Freezing it. Okay? You can write out a reaction. We've got H2O turning into H2O. It's not a very exciting reaction. One of these reactions, the reactant is liquid, and the product is a solid. You're freezing. Okay? The temperature is going down. Now, the question here is this process exothermic or endothermic? It's very weird.
So,
Yeah.
exothermic.
It's exothermic, which is weird because we always think this, that we should be feeling something really, 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 really hot. But in this case, it's an ice cube. So you're going from liquid. Yeah. So when you're freezing something, heat is being released. Because it is cold. It's getting colder. It's getting so cold that it's turning into ice. But it's giving off its heat to you. So this whole process here is exothermic. Do you like the freezing?
Ice cube.
Yeah.
It's
That's for you. No. Right with those on. It dries them out. Now, let's go the other direction. Let's say that we've got H2O liquid turning into H2O gas. Okay, these are phase changes. We're going from liquid, the L, to the gas. In this case, liquid has this energy, and the gas has a higher energy. So you're going to need to add more heat to turn it into gas. These types of questions, it's easiest just to write out what the reactants are. Is there going to be heat over here given off? Or is there going to be heat over here taken in? Are you going to need to add heat to make this work? Or are you going to need to, is heat going to be given off as a product? Okay, so this one's going to be yes, this one's going to be endothermic, which is weird, again, because if you're heating something up to make steam, you'd think it'd be hot, but it's just the fact that you're adding so much heat to the reaction that makes it suck in the heat and become gas. So we're considering here just the water. We're not talking about the surroundings, just the water. The water is turning into gas, so it's endothermic.
So you could still think of it as if you're like boiling water, you have to add heat to the water to make it
Right. Exactly. Exactly. Good. So that's endo, exo, those are the types of questions I can ask you. For example, I could say true or false, this is an endothermic reaction.